Today, what we're going to do is not continue to work with just the basic properties and transforms of the Z transform. They're very similar to the DTFT. I want to begin to get to how we actually make use of it. And what we're going to see today is some terminology and some functionality that is very, very similar, very parallel to what you encountered in continuous time systems when you're using Laplace transforms for system analysis. Today we're going to be talking about transfer functions, poles and zeros, all those same kind of concepts, and how we make use of them in system analysis for discrete time systems. So for discrete time, linear time invariant systems, the function h of z, capital H of z, is the moniker we use for the transfer function of the system. It's literally the ratio of the Z transform of the output signal divided by the Z transform of the input signal. It's also a Z transform. It happens to be the Z transform of the unit sample response. So there's no surprise that we use capital H for this. Little h of n, the unit sample response, is the time domain version of this. Its Z transform is capital H of Z, the transfer function. And as you are hopefully connecting, it's similar in usage to h of s, the S-plane version of the transfer function for a continuous time system. So all the things that we learned that we could do with h of s's, that kind of S-plane transfer function, we can do with the Z-plane transfer function for discrete time systems. And just as we found a shortcut way to get to the frequency response, the DTFT frequency response of a system directly from its difference equation rather than transforming its unit sample response with a DTFT transform, we can get to the transfer function h of z directly from the difference equation by using a similar process, just substituting the Z transform for the DTFT transform. So using the same example we did in DTFTs, if we have this single feedback IIR filter described by the difference equation y of n minus alpha y of n minus 1 equals x of n. And if we were asked to find the transfer function for the system, or we needed that for an analysis, all we have to do is take the Z transform of the entire difference equation, term by term by term, using linearity where we need to, where we're multiplying by constants, using the time shift property of Z transforms, and where we have time shifts. And so y of z transforms over, y of n transforms over to y of z. Y of n minus 1 transforms over to, well, y of z for the y of n part. The n minus 1 part, the time shift part, is z to the minus 1, and the alpha comes across as a multiplier. And suddenly we see that we're doing a Z transform back when we were trying to find the characteristic equation for a system. We were writing it out using this Z notation, and we were actually at that time taking a Z transform. On the right hand side, we transform y of n and get x of z. And now we can, as we do with the DTFT, extract the y of z out of the right hand side. And if there are any multipliers, anything more than the single x of z term on the right side, we would also extract the x of z. And we can create h of z as the ratio of y of z over x of z just by rearranging this relationship that leaves 1 in the numerator and 1 minus alpha z to the minus 1 in the denominator. So just by going through the simple process of Z transforming the difference equation, a quick bit of algebra, we've got our transfer function. So that's probably going to be the preferred way that we're going to want to do this when we need to find the h of z. Now, if we were to apply that same idea to a generalized difference equation, one that has lots of terms to it, we have all the y terms on one side in the standard form, all the x terms on the other side, all our y coefficients, we used the capital A for those with the subscript that goes with the delays. And on the x side, we used b coefficients with subscripts that match the delays of our x terms. If we took this whole equation and went through that exact same process, Z transformed it term by term, we would get something always of this form. Y of n would become y of z, a1 y of n minus 1 would become y of z times z minus 1 times a sub 1, and so on for all the terms. Same thing on the x side, we get capital B0 times x of z, b1 times x of z times z to the minus 1 to deal with this delay, and z to the minus 2 in the next term, and so on. And they will all have to have this same form. The only thing that would change is what were the b and a coefficients. We could still factor out the x of z from one side, the y of z from the other, and create that ratio. Y of z is h of z is y of z over x of z, and it must always have the same form. It's the left-hand side of the standard generalized difference equation without the x of z's, those removed, and in the denominator, the right-hand side of the difference equation with the y of z's removed. And so it will always be the difference equation coefficients with the b's in the numerator, the a's in the denominator, and a polynomial in powers of z. Now I could multiply these through. Then notice the numerator has a degree m polynomial in z, and the denominator has a degree n. If we were to multiply through by z to the n, we could have the denominator all in positive powers of z. And depending on which order was higher, n or m, you might have positive or maybe a few negative ones in the numerator. Now you can probably anticipate where this is going because we made these same arguments in 228 and said, okay, we've got a transfer function, let's factor the numerator and denominator because it's a polynomial in z. Particularly if we make it positive powers of z, then it's a little bit more obvious how to factor it. And if we did that, they always have to have some number of factors in the numerator and some number in the denominator, maybe a multiplier, a gain coefficient out in front. And we're going to name these factors, the z1, z2, all the factors that were roots of the numerator polynomial in z. We're going to call those the zeros of h of z, for the obvious reason that if I set z equal to either z1 or z2, then I'm going to get one of the terms in the numerator being 0, forcing the whole numerator to be 0. And as long as that term's not in the denominator, I'll have a constant of some form in the denominator. And so h of z, the transfer function, has to have and will always have a value of 0 when I choose z to be one of those roots of the numerator polynomial. Similarly, any root of the denominator polynomial in z, p1 and p2, we'll call those the poles of h of z. Those are the roots of the denominator polynomial in z. They're also the values that if we plug one of those into the denominator and the numerator term, so we set z equal to those particular values, we're guaranteed to get a 0 in the denominator, some non-zero constant in the numerator, and so h of z, for those values of z that are poles of the system, wants to go to, well, c over 0, which is infinity. So that's the name poles, like it's pushing it way up, 0 is like it's dragging it way down to 0. So here's an h of z, not in factored form yet. Z squared plus 1 over z squared minus 1/2 to the z. If I wanted to know where the poles and zeros of this particular transfer function were, I could factor the two polynomials. The top, we said z squared equal to minus 1, so z equals plus or minus j, purely imaginary. In the denominator, we have a common factor z I can bring out, so that factors to z over z minus 1/2. This system has two poles and two zeros, two roots in the numerator, two roots in the denominator. The two numerator roots are z equals minus j for this one, z equals plus j for that one. And the roots of the denominator, or the poles of the system, are z equals 0 for the first term, z equals plus 1/2 for the second term. Now, if you give me the poles and zeros of the system, plus one more piece of information, I can reconstruct h of z. And if I can reconstruct h of z, I can actually get back to my difference equation, or I could get back to my unit sample response by inverse Z-transforming it. So the poles and zeros with one more piece of gain information are actually a complete description of the behavior of the system. It gets me back to the difference equation, gets me back to the unit sample response. It captures all the dynamic behavior of the system. And so we can describe a system using a diagram, using a pole zero diagram that shows us where are the locations of the poles and the zeros of the system. Now we did this in 228. We had it in the S-plane. We had pole zero diagrams that had the S values of our poles and zeros indicated. We have the same thing here, except it's in the Z complex plane, where we have our real axis for the real part of Z. We have our imaginary axis for the imaginary part of Z. And the whole complex plane represents all the possible values of Z. The particular ones we want to denote here are which ones are roots of the numerator and denominator. So we'll also want to keep track of, for reasons we'll see in a few moments, of where are those poles and zeros relative to the unit circle. The unit circle, again, was the circle of radius 1 in all directions. So it passes through -1, +1, +1j, -1j. For our particular system, I have a zero here for z equals +j, so I'll literally draw a 0 at that position. I have a 0 at z equals -j, so I'll draw literally a 0 there. We have two poles, one at z equals 0, one at z equals +1/2. For poles, I'll use x's to indicate those on the diagram. So I'll have one at z equals +1/2 and one at z equals 0. And here's a pole zero diagram of my system. Now, this is telling me stuff about values of z. It's not telling me really about values of h of z. I still would have to do some mathematics to compute what is h of z, a complex function, what are its magnitude and phase at various values of z. And if I did that, I need another dimension. We've got two dimensions, the two flat dimensions of a diagram already taken up with just the complex value of z. H of z's magnitude and phase would have to be coming out of the board, coming out of your screen, as it were. So it would be a surface above or below this z-plane. And it might look like this if we looked at it on its side view, where our pole zero diagram, our z-plane's down here in the base. And this is actually a plot for that last function that we had, the magnitude of that function plotted versus all possible values of z on this grid here. And we see some interesting things about this. The surface that's created by the magnitude of h of z acts like a rubber sheet sitting above the z-plane when we plot its magnitude. And that rubber sheet is tacked down by the 0 positions. So when we plug in the 0 values of z, h of z becomes 0, so its magnitude is 0 also. And so we know that the surface has to touch down on the z-plane for those particular values. And for the poles, h of z's magnitude wants to go off to infinity. So we would want to see above those things like we see here happening, where the contour is going stretched off to the ceiling. So again, anywhere we had zeros, we should have the rubber sheet tacked down to the z-plane. Anywhere we have poles above there, we want to push that rubber sheet up to infinity, and then let the rubber sheet take its contour wherever it wants to go from there. Now I do need to constrain the edges of the rubber sheet, if you will. This particular one seems like it wants to asymptotically approach 1, and it does. What we would have to look at there is what does our function h of z do as z goes to infinity? And in our particular case, we had a z squared in the numerator, a z squared in the denominator, So as z goes to infinity, that tends towards 1. And again, this rubber sheet, this contour represents the value of the magnitude of h of z. As I plug in all these different values of z into it, its height is what the magnitude would be. So if I move over here to z equals 1 and see how high is the rubber sheet, in this case it's about a height of 4. If I take my h of z, plug in z equals 1, and see what the magnitude is, we should get that value. So let's take another example and get a little practice on this. Here's a transfer function, z squared, it's already factored for you, z squared times z minus j times z plus j, and the denominator a z minus a half, z plus 3/4, z plus 1 plus j5, and z plus 1 minus j5. Let's create a pole zero diagram for that particular system. I have 2 zeros from that z squared, 2 more zeros from here, and 1, 2, 3, 4 poles. The 2 zeros with the z squared term will happen at z equals 0. Notice if I have multiple poles or zeros, I won't draw 2 circles. Usually what we'll do is draw 1 or 1 pole and put a number by it to tell us what the multiplicity is, how many of them are there. So this 0 with the 2 represents the 2 zeros that come from the z squared. I have, in the next term is 0 at z equals plus j1. And in the final term, I have is z equals minus j1, so we'll draw those zeros in as well. Here we get a pole at z equals plus 1/2. Here I get a pole at z equals minus 3/4, so those are right on the real axis. And then we have a complex conjugate pair at z equals minus 1 plus or minus j5. So we go back to minus 1 plus j1/2 minus j1/2. And this would be the pole zero diagram for the system. And it turns out those pole and zero locations will determine what the dynamic behavior of the system is. Because from those, we will get back the difference equation coefficients. If we recombine these different factors into a polynomial, we would have the AKs and BKs of the difference equation. Now, if the h of z wants to go off to infinity at the pole locations, the roots of the denominator, what do you think about whether the poles are allowed to be located inside the region of convergence of h of z? Hopefully you're seeing that this is a mutually exclusive idea. Convergence, things tamping down, is not what goes on when things go off to infinity. So logically, it would seem that any values of z that make h of z go off to infinity, those values of z cannot be within the region of convergence of the transfer function h of z. So poles are important, they're excluded from the region of convergence. How about zeros? Zeros make h of z go to 0. Well, that's not a problem. 0 is not a problem for convergence. In fact, it's a good thing. And so zeros certainly are allowed to be inside the region of convergence. So back in the beginning, we drew some rules about the region of convergence, in which direction it went, whether we had a right-sided or left-sided or two-sided sequence, if you recall. For causal or right-sided sequences, we said the region of convergence was some ring and was from some inner radius outward. Now, if that's the case, and I know I'm not allowed to include any poles within my region of convergence, then if these were the poles of my system, I would know right off the bat where is the region of convergence for that transfer function. It can't include A, B, or C. all poles have to lie outside the region of convergence. And so if my system inherently has a region of convergence that goes outward, I can't start it till I get past this seed pole here. And so the region of convergence for a causal or a right-sided system's transfer function will always be from just outside the outermost or the largest magnitude pole location and go from there outward. So we find, in this case, we find C as the outermost pole, and the region of convergence would start just beyond C. Would not include C, we just beyond it and go from there outward. If we had an anti-causal or left-sided sequence, in unit sample response in this case, the transfer function would have a region of convergence. Well, we know for left-sided systems, the region of convergence goes from some radius inward. And again, if I'm not allowed to include any poles, my only choice is to go inside of the innermost pole and start my region of convergence there. And that is, in fact, how it works. If we have a transfer function that we know is anti-causal or left-sided, or comes from a left-sided unit sample response, we know the region of convergence has to start at the smallest or innermost pole and go inward. If we had two-sided sequences, meaning they went to 0 on both sides, then we recall we had a region of convergence that was like a ring, like a donut. And in this case, if I have multiple poles, that could be between the first two poles or the second two poles. Both are possibilities. So I'm going to need to know another piece of information in order to tell which one is it. And for that, we go back to our stability criterion for recursive systems. Again, we don't have to worry about non-recursive systems. They're always stable. For a recursive system, though, we said back in solving difference equation days that the system was stable if the roots of the characteristic equation had a magnitude that were less than 1. Remember what the characteristic equation was. We were actually taking the difference equation, and although we called them difference operators or time delay operators at the time, we were actually taking the Z transform of the left-hand side of the difference equation and setting it equal to 0 to find the homogeneous solution. Well, that left side of the difference equation with the y of z removed also gives us the polynomial in Z from which we get the poles. So saying roots of the characteristic equation is the same thing as saying the poles of h of z. They are the same thing. And so the criterion we had for the roots of the characteristic equation for a stable recursive system apply also to the poles. So finding the roots of the characteristic equation is the same thing as saying finding the poles of h of z. And transforming that original requirement for stability, that the roots of the characteristic equation be less than 1, means if I've got the transfer function of my system, I can look at the poles, and all the poles have to have a magnitude less than 1, because the poles are the roots of the characteristic equation. Or another way to say that in pole zero diagram form is all the poles have to lie inside the unit circle for a causal system. Now that's for causal systems. For causal systems, remember our region of convergence goes from some inner ring outward. And if we want the system to be stable, all these poles have to be inside the unit circle. That's equivalent to in continuous time systems, when we said for the S-plane pole zero diagram, all the poles had to be to the left of the j omega axis for the system to be stable. That's the equivalent of this criterion. For discrete time systems, all the poles have to be inside the unit circle if it's a causal system. If it was an anti-causal system, well, we know those regions of convergence go inward. In that case, we want all the poles to be outside the unit circle. And if it's two-sided, it can be either. It can be inside or outside, but the requirement is, as we see in this case, all these cases, the region of convergence includes the unit circle. And so that is our general stability requirement for a discrete time system. The region of convergence has to include the unit circle. And if it does, all our requirements are met. For a causal system, all the poles are inside the unit circle because the region of convergence starts just outside the outermost pole. And if it's going to encase the unit circle, the poles have to all be inside the unit circle. Likewise, if for stability a left-sided system needs all the poles outside the unit circle, then the region of convergence, if it's going to include the unit circle and it's going to start at the innermost pole, that's an equivalent criterion. This also helps me resolve the question of where is the region of convergence if I have a two-sided system that has more than two poles. We said it could be between A and B, or it could be between B and C. Well, whichever one is going to encircle the region of convergence, that's the region we choose if we know the system is stable. So to our lexicon of all the different ways we can describe mathematically the dynamic behavior of the system, the difference equation with an impulse response, with a transfer function, with a block diagram, with a frequency response, we add now a pole zero diagram. And if you give me any one of these, I can get around, I can find a way to all the others. Now, it might take 2 hops to get there, but I can always transform one system representation into another by some means. And we'd like you to be comfortable with all those different means. For example, if we're given the pole zero diagram and we wanted to get back the transfer function and then the difference equation, here's how we would do that. Basically, we would take the process we were doing before and run it backwards, again, analogous to what we were doing with DTFTs. Except again, I need one more numeric piece of information. Because my system may have some numeric gain to it, I need to know about that. So you give me the poles and zeros of a system, you give me one value of h of f or h of z, and I can get back the difference equation and transfer function of the system. Now here we go. We've got a 0 at plus j, a 0 at minus j, a pole at plus 1/2, a 0 at, a pole at z equals 0, and we want to know what's the transfer function of the system if its frequency response has a value of 0, a value of 4 at f equals 0, if the DC gain is 4. Well, we would take those poles and zeros and that gain information, start with a prototype of our transfer function that has a factor for each 0, a factor for each pole, and some unknown gain out in front. Then we plug in the actual pole and 0 gain values, plug in plus or minus j for zeros, plug in 0 and plus 1/2 for poles. Notice we have minus signs in these terms. And then cross multiply or recombine these into a polynomials. And we have the transfer function of the system, other than an unknown gain here, k. So we need a piece of information to determine that. If we were told, for example, at h of z at z equals 1 equals 4, then we plug in z equals 1 for into this equation for z and get 1 plus 1 or 2 in the numerator times k, get 1 minus 1/2 in the denominator, and that gives us 4k equals 4, so k must be 1. That was easy, that fell out. So we know h of z is z squared plus 1 over z squared minus 1/2 z. To get to the difference equation, I want negative powers of z. I want time delays, not time advances. So what we usually do is look in the denominator, see what the power of z is here, and multiply the top and bottom by the negative of that power of z. And when we do that, the z squared becomes 1, the minus 1/2 z becomes minus 1/2 z to the minus 1, and the numerator becomes 1 minus z to minus 2. We equate that to h of z as y of z over x of z. Then cross multiply y of z times the denominator equals x of z times the numerator. Distribute in our y of z's and x of z's, and we have the difference equation in its Z-transform version. So inverse transform each of these term by term. Y of z becomes y of n. Z minus 1 y of z becomes y of n minus 1 from the negative 1 delay in z. The minus 1/2 multiplier comes across. X of z inverse transforms to x of n. And z to the minus 2 times x of z transforms to x of n minus 2 for the minus 2 delay. We had a vector k value that was 1, so we didn't have any extra multipliers on the right side. And there we have it. The difference equation for the system that had that original pole zero diagram is this one. So we can run the process forward or backward. We can get from difference equation to transfer function to poles and zeros to transfer function back to difference equation, as long as I have that one more piece of numeric information on the gain of the system somewhere at some value of z. So here's a bit more complicated one. The one example we did for a pole zero diagram, we have 1, 2, 3, 4 zeros and 1, 2, 3, 4 poles. So I'm going to have a fourth order system, but the process is the same. We would just start combining terms. So the first two terms in the numerator would combine here. This complex conjugate pair would combine to this quadratic. These two would combine to this quadratic. And we combine the quadratics, multiply by the highest power of z in the denominator, which is minus 4. So z to the minus 4 over z to the minus 4. We would need to solve for k normally. Here we'll just leave it in as a constant. Do our cross multiplying, which gives us the Z-transform of our difference equation, and then just simply Z-transform term by term by term. And even this complicated one is pretty straightforward. Just a lot of algebra, but no calculus, which is nice. Now, is this system causal? Well, if you just gave me a pole zero diagram, I'm not sure I could tell. If I recovered the difference equation, though, I can look at that and say, yep, it looks causal to me. All right, if it's causal, what's the region of convergence of this system? Well, we have to find the outermost pole. Here's one at 1/2, here's one further out at -3/4, but here's these poles out here. And so I would say the region of convergence, it starts here, whatever this radius is, and goes outward from there because it's a causal system. And based on that, I would say my region of convergence does not include the unit circle, so this system would be unstable. Or I could have just surmised that from the fact if I knew I had a causal system and I had these poles outside the unit circle, it's also automatically unstable. So we can do a lot with these transfer functions with poles and zeros, we can get back the difference equation, we can describe the dynamic behavior of the system, and we can also do some system analysis. Right? You've given me a description of the system's dynamic behavior. That's the transfer function, h of z. You give me an input signal. Okay, I can take its Z-transform. So for relaxed systems, we can certainly do zero-state responses. We can do convolution. We can do it in the Z domain, just like we did in the DTFT domain, by taking the Z-transform of the unit sample response, the Z-transform of h of n, which is h of z, the transfer function, take the Z-transform of the input, and multiply those together to do convolution, and then inverse transform the result to get y. We could do that with Z-transforms, or we could have done that with DTFT, so we didn't need a new transform for that. What we did need a new transform for was finding the total solution, including the initial conditions, getting that last missing piece, the zero input response. For that, I'm going to need not just the Z-transform, but a special flavor of Z-transform, the one-sided causal version of the Z-transform. We're not going to get to how we do that and how we use that till probably next week, but we will get there. Another thing we can do, if given the transfer function, is find the unit sample response or the impulse response of the system. That's just the inverse Z-transform of h of z. We can also reconnect with the DTFT and do all the stuff that we can do with DTFT, we can do with h of z. We can do with the Z-transforms. We can find steady-state responses of systems. And all we need to know is that relationship connecting the Z-transform to the DTFT. We can also surmise it when we understand the connection between poles and zeros and what effect they have on the frequency response of the system. For that, we need to know what this relationship is. What the different values of Z have to do with the shape of the magnitude or phase response of a system. For that, we'll talk about a graphical approach to analyzing a system and finding its frequency response. Ultimately, we'll want to take that information, that understanding of how poles and zeros shape the frequency response of the system, and use that to actually start designing filters, designing discrete time systems, using the locations of the poles and zeros as the basis of our design. Now, all of these require knowing how to do an inverse Z-transform. And we haven't gotten to that yet. We need to cover that. Next time, though, we will be able to tackle this, this relationship between the Z-transform and the discrete time Fourier transform. We'll be able to find the steady-state response of systems and their DTFT from the Z-transform. So what we'll do next time is reconnecting the Z-transform to the DTFT, look at how we approach analyses that we could do with the DTFT using Z-transforms, and then we'll introduce the inverse transforms and get to how we do relaxed system convolution, zero-state responses with Z-transforms, how we can find unit sample responses from the h of z transfer function, and then we'll move on to how we can find the total solution using initial conditions in a one-sided Z-transform.